In this lecture, we discuss what are the consequences of a Lagrange's theorem. So, yesterday, in the last lecture, we have to study here. So, what is the Lagrange's theorem? So, if S is a subgroup of a finite group G, then order of H divides order of G. So, what is the relation between the order of subgroup H and order of G here, okay? And we see also the consequences of Lagrange's theorem. So after then we study what is the index of a subgroup. So if G is a finite group and H is a subgroup of G, then the number of distinct right cosets or left cosets, the number of distinct right cosets and left cosets is called index of H, subgroup H in G. So we study the definition of index of a group, and we take one more corollary of Lagrange's theorem. So that is consequence of Lagrange's theorem. So what is the corollary we study here also? The index of any subgroup of a finite group is a divisor of the order of the group. We also prove that the corollary here, and we take the example of the Lagrange's theorem here. So this is a very simple theory. So we take another consequence of Lagrange's theorem. So what is the corollary 3? If G is a finite group, and A is an element of G, then order of A divides order of G. Okay? Order of A is the element of G. So we write here, so what is the Lagrange's theorem? So that is the order of H. For our reference, so that is divides order of G here, okay? Order of G. So this is the Lagrange's theorem, okay? So this is the Lagrange's theorem. So what is the consequence of Lagrange's theorem? If G is a finite group and A is an element of G, then order of A divides order of G, okay? So proof, let G be a finite group. So that is given. So G is a finite group and A is an element of group G. So we know that the order of an element of a finite group is finite, okay? So what happened here? We know that the order of an element of a finite group is finite. So if A is an element of a group G, then what is the order of A? So let us suppose here order of A is M. What is the order of A? Order of element A is M. Means order of A is M means A raised to M is the identity element. Then this M is called here order of that element. So the reason is given here. So what is the order of A? Order of A is equal to M. So we suppose here order of A is M. Then A raised to M. So that element raised to M is equal to identity element. Then M is the order of A. Okay. So now we consider the cyclic group generated by element A. So we consider here the cyclic group generated by element A is the subgroup of G. So what is a cyclic group? So this is a cyclic group. Cyclic group is what? Put A raised to 0, that is 1. Then A raised to 1, A raised to 2, A raised to 3, and so on. A raised to M minus 1. A raised to M minus 1. So this cyclic group generated by A. So how many elements are there? 1, 2, 3 and M. So in this cyclic group, there are M elements are there. So this is a subgroup of G. This is also cyclic group is a subgroup of a group G, where A1, A square, AQ, A raised to 1, A raised to 2, A raised to 3, A raised to M, is equal to, so that is equal to E. Means A raised to 0, that is 1, and E is identity element, so that is 1. So A raised to M1 is, A raised to M is 1, A raised to cube is 1, A raised to 2 is 1. Okay. So in this cyclic group, so the elements are in this form here. So this is a cyclic group, and this is a subgroup of the group G. So now we prove here the order of that element divide the order of group G, order of group G. So therefore, if order of A is M, order of A is M, and there are M elements are there, so certainly the order of that cyclic group is also M, and this is a subgroup. So this is also, we say this is H something, so this is H, so this is subgroup of group G. Then by Lagrange theorem. So what is the Lagrange theorem? If H is a subgroup of G and G is a finite group, H is a subgroup of G, then order of H divides order of G. So similarly, so this is also subgroup. So this is also subgroup of group G, then by Lagrange's theorem. So order of cyclic group divides order of G. Order of cyclic group divides order of G. So what is the order of this? Is M. So what is the order of this? Order of A is M. So this implies that order of A divides order of G. So proof is very simple here. We're taking, for example, a cyclic group and prove that this theorem. So what is the theorem? If G is a finite group and A is an element of G, then order of A divides order of G. So this is a corollary 3 here. Okay. So what is the corollary 4? What is the corollary 4 here? So this is also very simple corollary. If G is a finite group of order n, G is a finite group of order n, then for all A belongs to G. So for all A belongs to G, A raised to n is equal to E. So that is proving here. A raised to n is equal to E, where E is identity element. Okay, is an identity element. So again repeat here, what is the corollary? If G is a finite group of order n, then for all A belongs to G, then prove that A raised to power n is an identity element. So that is proving here. Okay. So what is the proof of this corollary? So let G is a finite group. Let G is a finite group and A is an element of G. Suppose order of A is n. So order of A is n. So that is n. Okay. Order of A. So we discuss what is the order of a group. What is already previous lecture. So suppose order of A is n and order of G. So yeah, order of G is n and order of element A is m. Okay. Then by this corollary, order of A divides order of G. Okay. By using this corollary, order of an element divides order of the group. So okay. So this implies that. So what is the order of A? So order of A is m. So then what happened? Order of A is m. Then m divides n. This is n. So m divides n. So okay. So if m divides n, so implies that n is equal to mk. So this is a division algorithm. Okay. If r is equal to 0, then what is the division algorithm? So we taking the definition of we take the definition of a division algorithm. So if m divides n, then n is equal to mk. So this is very simple here. How it is? How we can write this? So for example, something 2 divides 8. 2 divides 8. Okay. So then we can write this as, so this implies that what? This implies that 8 is equal to, so this is what? M. This is N. N. Then what happened? So this, therefore N 8 is equal to 8 is equal to what? So 2 divides 8 means 2 4s are 8. So then what happened? 8 can be written as something 2 into 4. 2 into 4. Okay. So what is 2? What is 2? 2 is M and this is K. So this is very simple. This is very simple. So M divides N implies that N is equal to Mk for some positive integer K here. For some positive integer K. So then we take power of A raised to N. A raised to N here. Okay. So what is N? N is Mk. So A raised to Mk. Put N is equal to Mk here. So this can be written as A raised to M raised to K. A raised to M raised to K. But what is A raised to M? So A raised to M is E. A raised to M is E. So this is E raised to K. So E raised to K is E. So that is identity element. Hence we prove that A raised to N is equal to E. And this is proving here A raised to N is equal to E. So what is N here? N is the order of G. So this implies that A raised to order of G is an identity element. So the proofs of these two corollaries are very simple. So yesterday we discussed what is the Lagrange theorem and what is the proof of Lagrange theorem. Then what is the index of a subgroup of H in G. Also we take examples and we taking here the consequences of the Lagrange's theorem here. So this is a very simple. Okay. So then what is the Euler phi functions and what is the Euler's theorem? So before that we're taking some definitions. Okay. Simple definitions. So what is the congruent modulo definition? We revise here the definition. So already we discussed in the last semester what is the definition of congruence modulo, but it is necessary to repeat the definition of the some definitions because to understand better here. So just revise here. So what is the congruent modulo N? Congruent modulo N here. Okay. What is the congruent modulo N? So let AB are the integers. Let AB are the integers. Then element A is said to be. Then element A is said to be congruent to B. Is said to congruent. Is said to congruent to A to B modulo N if N divides A minus B. If N divides A minus B. So A and B are the integers here. N integers and N is also integer. Then if N divides A minus B, then A is set to congruent to B modulo N. So what is the notation of that? So that is the notation is simply A is congruent to B modulo N. Modulo N. Okay. So A is congruent to B modulo N. So we took a very simple example. So what happened here? So something we take example. So take A is equal to something 5. Okay. A is equal to 5. Something B is equal to 15. Take So n is equal to 3 here. N is equal to 3. Very simple example. So what happened? N is equal to 3. So what is B? It's just this is A. This is a B. This is A. Or okay, you can take also A 5 minus 15. No doubt here. So that is this is A. So what is A minus B? So 15 minus 5. So just so. No. 15 minus 2 here. Taking n is equal to 2. N is equal to 2. So A is 15, B is 5, n is equal to 2. Okay? So what happened here? So what is n? 2. N is 2. 2. So that is A is 15, B is 5. So then what happens? So this implies that 2 divides 10. 15 minus 5 is 10. 2 divides 10. 2 5 are 10. Okay? Therefore we say that 15 is congruent to 5 modulo n modulo 2. Modulo 2 here. Okay? This is a very simple definition of congruent modulo n. So we already discussed here. So what is the congruent modulo n? Okay. So also we take a definition. What is the and theorem? So that is theorem. What is the theorem here? So theorem is what? So division algorithm. What is the division algorithm? So it is a very simple concept here. So and how to prove the theorem division algorithm in real analysis also here. So it is not necessary to prove the division algorithm here. In the last semester we discussed about the what is the division algorithm theorem and proof of the theorem here. Okay, so it is not necessary to prove here because this is not a part of algebra here. So just we taking the formula to prove another theorems here. So that is we have to revise the theorem and some definitions here. Okay, if A, B, C are the elements, if A and B are the integers here, A and B are the integers, and the B is greater than 0. B is greater than 0. Then there exists. Then there exist. Then there exist unique integers. Q and R such that Q and R such that A is equal to BQ plus R, where R less than equal to R greater than equal to 0 and strictly less than B. Strictly less than B. So A is equal to BQ plus R. So this is a division algorithm. So we prove this division algorithm in analysis. So that is this proof is already taken here. So we just discuss what is the division algorithm here. Okay. So for example we take here. So very simple example. So then what happened here? So just A is equal to taking A is equal to 15. A is equal to just A is equal to 15. So something B is equal to something 2. Then what is the Q and R? So that is 15 divided by, what is the 15 divided by 2? Okay, 2 7s are 14. So that is 1. Okay, 1. Then what happened here? So that is A is what? So A is 15, B is 2, 7 is what? Q. And R, this is the remainder. Okay. So this, what happened here? So that is 15 can be written as, 15 can be written as, what is B? B is what? 2. What is Q? 7. Plus R is remainder. So okay, R is remainder. So what is R? R is greater than or equal to 0. And R is less than B. B is 2. So this is division algorithm. Okay. So just what is, we take the next definition. What is Euler's functions? First you understand the simple definition, simple concepts. Then it is easy to understand the proof of the theorem. Okay, proof of the theorem. Okay. So what is Euler's phi functions? What is the Euler's phi function? Euler's phi functions. Okay. The Euler's phi function definition. The Euler's phi function. So we define for any integer. So phi n. So we say that is a phi n Euler's function. Okay, phi n is defined for all positive integer. For all positive integers. By. So we take a definition. What is the definition? What is the Euler phi function here? Okay. So phi of 1 is equal to 1. Okay. Phi of 1 is equal to 1. What is the phi function, Euler's function? So we understood better here that definition by taking examples, very simple examples. So phi of 1 is equal to 1. So n is equal to what? N is equal to 1. Then phi of 1 is equal to 1. But if n is greater than 1, then n is greater than 1. N is greater than 1. So phi n. What is phi n? Phi n, the number of positive integers. The number of positive integers less than n, what is n? This n, so which you have to take a number integer, that is n. So phi of n, the number of positive integers less than n and relatively prime to n. Relatively prime to n here. Okay, very simple. Definition is very simple here. Okay. So how to understood this definition? By taking example. So this is a better way. First we take an example and then understood the definition. Okay. So for example. Okay. So phi of 6. What is n? N is 6. So phi of n is 2. Phi of n is 2. So what? So phi of 6. So this is Euler function. So pi of x is equal to 2. Why? Because the positive integers definition. What is the positive definition is given? Positive integers less than positive integers less than 6 are what? Less than 6 are what? 5, 4, 3, 2, 1. So these are the integers less than 6. Okay? 5, 4, 3, 2, 1. 5 integers are there. But so find those number relatively prime to n. So what are the integers which are relatively prime to 6? So there are, so whatever, but the relative prime to 6 are 6 are. So the relative prime to 6 are the integers which 5 and what 1. 5 and 1. Why 5 and 1 only? Out of these, only 2 numbers 5 and 1 are relatively prime to 6 because GCD of 6 and 5 is 1. Because GCD of 6 and 1 is 1. Okay, greatest common divisor. Why not 4? Because GCD of 6 and 4 is 2. So this is not allowed. So how many numbers are there? 2 numbers are there. So what is the pi of 6? That is 2. So pi of 6, that is 2. So the Euler function of 6, Euler function of integer 6 is 2. So there are 2 numbers are there, 5 and 1. So GCD A and B are relatively prime. A and B, B 2 numbers, A and B are relatively prime if GCD of AB is equal to 1. Okay, so pi of 6 is equal to 2. Then also we discuss, so we take another example. So what is the pi of 6? Pi of 8. So pi of 8, what is the Euler function of 8? Pi of 8 is equal to 4. Why? Because the positive integer less than 8 are 7. Less than 8, 6. What are the integers? Less than 8, 7, 6, 5, 4, 3, 2, 1. Okay? So, but the relatively prime to 8 are what? 8 are what? So, which are the numbers relatively prime to 8? So that is 7. Then 5, then 3 and 1. So 8 is relative prime to 7, 8 is relative prime to 5, to 3 and this is 1. So how many integers are there? So that is 4. So pi of 8 is equal to 4. So this is the definition of, very simple definition of Euler's pi function here. So we take, so what are the Euler's theorem and Fermat's theorem? Okay, Euler's theorem. So you understand what is the pi of n here. So what is the theorem? Euler's theorem. Euler's theorem. What is Euler's theorem? Okay, if n is any positive integer, if n is any positive integer and a is any relative prime to n, relative prime to n, then a raised to Euler's function pi n is a congruent modulo to 1. A raised to Euler's function pi n is congruent to 1 modulo n, where phi n is Euler function, where phi n is Euler function. Okay, so this is the Euler's theorem here. So what is the proof of that theorem? Proof is also simple. Also, what is the Fermat theorem? Fermat theorem. So if a is an integer, is any integer and some p, and p is prime, p is a prime, then so this is a consequence of Euler's theorem. Fermat theorem is a consequence of Euler's theorem. Then a raised to p congruent to a modulo p. So these are the Euler's theorem and Fermat theorem. So how to prove to the next lecture. Thank you.